So we shall start with the next concept, design of binary counters. So for in the previous videos what we discussed was it was shift registers. Okay, so this is counters. Counters is something where each counter is something it will be keep on counting either in upward direction or it might be in a backward direction. Like if it is mod 8 counter, 8 counter means so it starts from 0 and then it will be 1, then 2, then 3, then 4, then 5, then 6, then 7, up to 7 if it is mod 8 counter. If it is mod 5 counter, it will display up to mod 4 and it will go back to 0 again in a cyclic manner. If it is mod 8 counter, it will start from 0 up to 7 and it will go back to 0. If it is mod 16, it will display up to 15 and it will go back to 0, like this. Counter means it will be keep on counting in a sequence manner. Okay, so counters are also same as well, the registers. So counters are also made up of flip-flops. Okay, so here counters are made up of flip-flops, right? Here we have two types of counters. One is synchronous counter and asynchronous counter. What is the difference between synchronous and asynchronous means? In case of synchronous counter, the counter which changes its state like 0 to 1, 1 to 2, like this counting sequence from 0 to 1, 1 to 2, 2 to 3, 3 to 4, like this, which changes its state with respect to the clock pulse. That is what we call as synchronous counter. So asynchronous is something which doesn't take the clock pulse into the consideration. That is what we call as asynchronous counter. Okay, so now we shall go with one example. So here we are supposed to construct a binary counter which should display so from 0 to 7. So but we need to construct this binary counter by using T flip-flop. Okay, so T flip-flop, you need to remember how the T flip-flop is going to work. Okay, so first how it should see, like first CBA, first it should display 0 0 0. Next after the next clock pulse it should display 0 0 1. After the clock pulse it should display 0 1 0, then 0 1 1, then 1 0 0, then 1 0 1, then 1 1 0, then 1 1 1. It should start from 0 0 0, then 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1. So it's like 0 to 7. This is a mod 8 counter. We call it as a binary counter. Okay, so this is how it's supposed to be. We are supposed to construct a circuit by using T flip-flop. The output should when we press the clock pulse for the first time, it should display 0 0 0. So next clock pulse it should display 0 0 1. Next clock pulse it should display 0 1 0, like this. Okay, so how to construct this circuit now then? So look at this table. So here we have three columns. One is present state, next state, and flip-flops inputs. Okay, so what is the present state now? So look at here, present state CBA 0 0 0 0 0 1 0 1 0. This is how the counter has to be give the output. First it should give 0 0 0, next 0 0 1 0 1 0. This is how. So if 0 0 0 is the present state, what should be the next state after giving the clock pulse? It should move to 0 0 1, right? So that is what they are given. The present state is 0 0 0 means next state is 0 0 1. If the present state is 0 0 1 means the next state is 0 1 0. If the present state is 0 1 0, next state is 0 1 1. If the present state is 0 1 1, next state is 1 0 0. So if the present state is 1 1 1, so this is 7. So after completing 7, it should go back to 0. So 0 0 0. So this is a present state, this is a next state. So present state we normally represent as CBA and the next state we normally represent with a plus, like C plus, B plus, A plus. Okay, this is how you're supposed to write. And flip-flop inputs. Okay, so you should notice here when it comes to A flip-flop, when it comes to A will change for every clock pulse. So for the first clock pulse A is 0. For the next clock pulse it will be 1. For the next clock pulse it will be 0. For the next clock pulse it will be 1. For the next clock pulse again 0, next 1, 0, 1, like this. For every clock pulses, A is going to change its state. Okay, 0, 1, 0, 1. For every clock pulse, A is going to change its position, changes its input data. 0 to 1, 1 to 0, again 0 to 1, 1 to 0, like this. When coming with B will changes its state whenever A is 1. B will changes its state. Right now B is 0. So next B is, again it remains in the 0 because A is 0. B will only changes its state when A is 1. Look at here. So when A is 1, B will changes from 0 to 1. So clear? So A will changes its state every time. Every clock pulse A will changes its time. B will changes its time only when A is 1. Okay. So look at whenever A is 1. A is 1 here. So B changes from 0 to 1. Okay. So next again A is 1 here. So B changes from 1 to 0. So A is 0. So B remains in the same state. 0 again 0. So A gets 1. Again B changes from 0 to 1. So A is 0, so again B remains in the same state like this. Similarly, C changes its state when both A and B both are 1 and 1. Whenever A and B are 1 and 1, then only C changes its state. C, look at it, C is 0, next 0, 0, 0. C never changes here. Why? Because A, B is not 1 and 1. So C changes from 0 to 1 when A, B is 1 and 1. See, look at here, A, B is 1 and 1. So C changes from 0 to 1. Okay, next again AB is 1 and 1 here, so next it will be 0. So like this. So this is how this is going to work. Okay, so we are supposed to write what is TA, what is TB, what is TC. Okay, before writing this we need to know how the T flip-flop is going to work. Okay, T flip-flop. Do you remember T flip-flop, how it is going to work? So look at the T flip-flop. When inputs, when the inputs both are 0 and 0, so if both the inputs are same, the output will be 0. If both the inputs are same, 1 and 1, output is 0, 0 and 0, the output is 0. If both the inputs are same, the output will be 0. If the inputs are different, 0, 1 and 1, 0, the output will be 1 and 1. Remember this truth table, T flip-flop. If the inputs are same, the output will be 0. If the inputs are different, the output will be 1. This is how the T flip-flop is going to work. So based on this, so we need to compare the present state with the next state now. So compare this A with A plus. Present state is A, next state is A plus. What is present state here? 0. What is next state here? A, 1. So 0 and 1 are the two inputs for the T flip-flop. So if the inputs differ, the output is 1. So only concentrate on A column, A plus column. So look at this A and A plus and fill TA. Concentrate on B and B plus, fill TB. Concentrate on C and C plus, fill TC. Like this, okay? So concentrate on A. What is A? 0 and 1. If both the inputs are different, according to T flip-flop, the output is 1. So here 1, here 0, the inputs are different, so 1. Here 0, here it is 1, so the inputs are different, 1. So here 1, it is 0, so inputs are 1. So for every inputs A and A plus, the inputs are differs, so all the TA will be 1 and 1 and 1. Like this. So let's compare B. Here it is 0, again here 0, both the inputs are same, the output will be 0. Here it is 0, here it is 1, the inputs differs, so the output is 1. Here it is 1, here it is 1, both the inputs are same, so the output is 0. If the inputs are same, the output will be 0. If the inputs are different, the output will be 1. Same. So look at here, see. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 0, 1 and 1, same inputs, 1 and 1, so 0. 1 and 1, 0, 1 and 1, 0, 1, 0, 1, like this. Okay. So once you are done with this table, you need to construct a K-map for TA column, TB column and TC column. So anyway, TA column is filled with, you need to construct a 3 variable K-map because we have 8, 1, 0, 0, 1, 2, 3, 4, 5, 6, 7. So 0 to 7, 8 boxes. So you need to construct a truth table like this. This is a 3 variable K-map. So we don't have a K-map for TA because look at TA, all are 1. So if you fill the K-map with ones, only once, you can group an octant, a single group, like whole K-map is filled with ones. You can make a big group, that is octant group. If you make a one complete group like this, then TA will be 1. TA is equal to 1. Okay. So let's concentrate TB 0 1 0 1 0 1 like this. So this K-map should be filled with like this. This is 0th position. 1 2 3 4 5 6 7. So look at here. 0 1 2 3 4 5 6 7, right? 0 1 2 3. So here 0 1 2 3, not 0 1 2 3. It's not 0 1 2 3. It's not in a sequence manner. First it is 0, this is 1, this is 2, then go back 3 4 5 6 7. So fill this column with this respect to K-map and make a group. Here one quad is possible. So TB is equal to this 0 1 get cancels, this 0 1 get cancels, this is A, that is A. TB is equal to A. TA is equal to 1 because octant is possible. When whole K-map is grouped, by default it will be 1. So TA is equal to TA is equal to 1, TB is equal to A. Okay, by grouping this. Then TC, a single pair is possible. 0 1 cancels, this is AB. TC is equal to AB. This is the equation you got for TA, TB, TC. So using this, you need to construct a circuit by using T flip-flops. I have used it's a 3-bit binary counter. Why it is 3-bit binary counter? Why you are supposed to use 3 flip-flops? Because look at this, it is supposed to display from 0 to 7. So 0 to 7 means nothing but 8. Nothing but 8, that is 2 to the power of 3. It should start from 0 to 7. So 3 flip-flops, you need 3 flip-flops. So they have specified which flip-flop you are supposed to use, that is T flip-flop. So they have used A flip-flop, B flip-flop and C flip-flop, 3 flip-flops. All are TA, TB, TC. All are positive edge triggered. T flip-flop works with respect to positive edge trigger. So there is no bubble. All of them are connected to the clock. Okay. So then, we came to know that what is TA? TA is equal to 1. So connect TA is equal to 1. Just write 1. So then what is TB? TB is equal to A. So TB is input A. So take a connection from A. This is A and this is A bar. Take a wire from A, connect to TB. Okay. Similarly, TC is equal to AB. TC is equal to AB means you are supposed to use a NOT gate. This is A, this is B. The output will be AB like this. Okay. So TC. So AND gate, one input is from A, another input is from B. So this is connected to TC. This is how you are supposed to construct a synchronous binary counter by using T flip-flop. Okay, the same explanations they are given here. We can go through this explanation, whole explanation. So next week we shall deal with how to construct the same synchronous binary counter by using D flip-flop. Okay, by using D flip-flop. Okay.